So here we introduce the deep learning with Python, and we nominate it or the title or the subtitle from classical machine learning to neural network. That's what you have seen yesterday, and one of you has presented on classical machine learning with application for loans. And our agenda today, let me just So the agenda today, we are just going to see, we have the title, the agenda, and the learning outcome, which is an overview. The setup and environment check, which is technical. And we are going to talk about the from classical machine learning to deep learning, which is conceptual, the neural network fundamentals itself. And we are going to see the feed-forward neural network, the recurrent neural network. Maybe not today, because all this is too quite big. And after that, the convolutional neural networks dealing with most of the images. The recurrent neural network is dealing most of the temporal or recurrent data. And we have the model evaluation and troubleshooting. This is theory plus code and the mini projects. And at the end, it will be wrap up and further reading. So we are going just to take the point 1 to 5, and then going to 8, the model evaluation for the 5, and then mini project and wrap up and further reading. So about the learning outcome, by the end of this notebook, the aim is just to be able to explain what a neural network is and describe how it's learned from data through forward propagation, loss computation, and back propagation. All those concepts, we are going just to see them once we are continuing with the practice. And the second outcome is to distinguish between 3 fundamental deep learning architecture. So we are obliged to distinguish, to make a clear distinction between all those 3 fundamental deep learning architecture, the FFNN, the RNN, and the CNN, and to identify which one is best suited for. So after that, to build from scratch using the tensor of Python. And we cannot just also to interpret and the accuracy plots, and to diagnose common problems such as underfitting, overfitting, and unstable training. All those concepts, we are going to see them properly. And then to apply regularization techniques. So in case when you meet underfitting or overfitting or unstable training, you need to regularize your model by using some technique like dropouts. And we are going to see all of them: early stopping, patch normalization, in order for you to improve the generalization of your model. And at the end, to compare and contrast deep learning approach with the classical machine learning methods, covering week 5, understanding when each approach is appropriate. So how to use this notebook? So this notebook is serve 3 purposes: as a lecture resource, as a coding lab, and also as a reference. You are going to see that is really really complete. So you have everything inside this notebook. So now let us start by set up our environment. So we need just to there is some explanation before going to set up and know the environment. Let me check here. So in week 5, you train model like random forests and SVMs. That's what I've seen one of you have done yesterday by using logistic regression for the case of loans and everything. So those algorithms, machine learning algorithms involve relatively modest computation. It means if you have a laptop CPU endless, it will handle them easily. So for deep learning, it's different because here we may have millions of parameters. The parameters that we call at the same time the weight. And training involved repeating matrices, matrix multiplication across thousands of data samples for dozens of or hundreds of epochs or the iterations. This is an enormous amount of arithmetic. So that's why you need most of the time or for the deep learning, you need GPUs. And for this one, maybe the appropriate environment to use is the Google Colab here because it gives us or provides free access to a GPU. And then for just to enable this GPU working, you just go to run time in the menu bar. Let me open my Colab here. So for those who are using Colab, because I'm not using Colab here. So you need to enable changing the runtime. You can see here, let me just, it's 120. Okay, you go to connect and then change runtime type. And here you can select maybe T4 GPU. This version is just going to help you to run as directly here. So you click on save and then you have everything with you. So let us start here by importing all required libraries. So you have some libraries here. Hope that you have already used those libraries when doing machine learning. So it will be almost the same, but just to explain as fast as possible, you have some of those libraries, like NumPy, but it's coded here as NP. Pandas is coded as PD. Pandas NumPy for manipulating array and doing computation, and matplotlib for plotting, and you have the scikit-learn itself for the classical machine library. You already know it. And you have the TensorFlow and Keras. This is our deep learning framework. So you call the TensorFlow as TF. And from TensorFlow, you can import Keras. So those are the important library to use And then after importing them, you can now run this code. So you can see here, you print all the library imported successfully. Let us run it. So you have all the library imported successfully. You have the Python, the NumPy, Pandas, TensorFlow. The Keras here, we have it, but not the version behind 3. So we have version of 2 point something. So we can check also the availability of the GPU. So just run this code so you can see the availability of your GPU. Just for me here, there is no GPU detected. So the training will use a CPU. And so if you change it, but here I'm just using directly a Jupyter notebook. That's why I'm not using a Colab. So we have this one. So the next step is now to set random seeds for reproducibility. So the neural network involves random initialization of weight. So we need random initialization. Yesterday, one of you was asking the professor about how the weights are set in the neural network. There is only an initialization, a random initialization of weight. After this initialization, the weights are just set on the network automatically. So we use the seed 42. So if we don't use this seed, so we are going to see maybe like here, we say NP random seed or random set seed. Sometimes when we are just running, we are getting different results. So even you are going just to get different results from me. And then at the end, we will not have the same result, all of us. But if we put the seed on 42, so all the time that we are going just to reproduce our computation, we are just going to obtain the same result as before. So we configure the matplotlib for clean, readable plots. And then we run it. So the random seed here is set to 42, and the matplot default configure for presentation quality plot. So once we have all this, and we are just going to plot and have the same type of figure, the same type of plots, the same size and everything. So our checkpoints 2.1 is the question, why are GPUs faster than CPUs for deep learning? And why do we set random seeds? I just answered to this question. What would happen if we did not? So all those questions is just for you just to remember, why is it important to use GPU instead of CPU for deep learning? So the hint here is to think about parallelism. So section 3, from classical machine deep learning to deep learning. Here we are just going to understand why deep learning exists and when to use it, just as important as knowing how to code it. Okay. Okay, a quick recap of week 5. For week 5, if you remember, even what one of you have done yesterday, you learn the standard machine learning workflow. So how was the workflow? You have a raw data in a data frame, and you do some feature engineering. It means You just maybe created new data or new variable from the initial variable. You clean the data, you do everything. So after that, you can now train your model, and you evaluate your model on the testing parts, not the training, because the training is just for just modeling. And then after evaluating, if you find good results, you can now deploy your model, and your model can work and do the job. So you worked with algorithm included linear regression. So linear regression was just for predicting continuous values with a best fit line. Logistic regression is a kind of linear regression, but this one is just for predicting binary classification. But here we are using the sigmoid function, and we also deal with decision trees, where we was splitting data based on feature threshold, and the random forest, which was an ensemble of decision trees for better generalization, the SVM or super vector machines for finding optimal decision boundaries, the KNN that we call K nearest neighbor for classifying based on nearby example. And all those methods share a critical assumption. The critical assumption is what? You, the human, must design the input features. So you are the one who you must design the input features. So this is the critical assumption for machine learning. You decide what column to include, how to encode categories, what ratios to compute, and what transformation to apply or not to apply. This process is called feature engineering. And it is often the most time-consuming and expertise-dependent part of the machine learning pipeline. And here, something to add is about also depending on the domain. The feature engineering depend also on the domain. Maybe when you are in finance, you are not using your feature engineering your feature at the same level as someone else in another field. So there may be some assumption to check first. So now the feature engineering bottleneck. So for the feature engineering bottleneck, it's work well. It's work well with for structured or tabular data. If the data is structured, tabular, and this feature engineering is going just to work well. So, for instance, you want to predict house price. You want to predict house prices. You know that square footage may be the number of bedrooms and location matter. So this will help you to predict house prices. So this is structure. This is tabular data. You want to detect maybe the email spam. So you can count specific keywords, maybe check sender reputation and measure link density. So those are structured tabular data where the domain knowledge tell you what feature matters. But what about this task? If maybe you want to classify photographs of cats vs dogs, are you still using structured or tabular data? So what feature would you craft? So the pixel values alone are meaningless. So a slightly shifted photo of the same cat produce a completely different pixel vector. So you would need to detect age, You would need to detect textures, shapes, and spatial relationship between parts. So this will help you to design these features by hands. If you want to design this feature by hands, it will be extraordinarily difficult for you to do. It's not like the structure of tabular data. If you want to detect to by hands to do like to know the square footage, the number of beds, location matter, this can be doable. But for classified photograph of cats and dogs, vs dogs, it's extraordinarily difficult. Maybe another task is when they ask you to determine if a movie review is positive or negative. Think about it. You have a movie, so you need to review if it's positive or negative. You could count positive or negative words, maybe, but the language is subtle. This movie is not bad, is positive despite containing notes and bad words, order, context, negation, and sarcasm all matters. Imagine all those elements. So handcrafting features for all these linguistic phenomena is unpractical. So this is not tabular, this is not structured. If you want maybe to translate a sentence from English to French, imagine the complexity. It requires to understanding the grammar, the vocabulary, the idioms and context at the level that no handcrafted feature set can capture. These tasks share a common property. The useful features are complex, hierarchical, and hard to articulate. This is precisely where deep learning excels. So for all those type now of complex activity or complex prediction, classification, you need now deep learning because machine learning is really limited. So now the core idea of deep learning. The core idea of deep learning is what we call the representation learning. Instead of designing features by hand, let the model learn its own feature directly from raw data. So the model is just going to learn its own feature directly from raw data. And then it's just what we call the representation learning. Instead of designing features by hand, as we were doing in machine learning, that's what we call feature engineering. This one will be different. This is called representation learning. A deep learning network does not just learn a mapping from feature to labels. It's learned to transform the raw inputs into increasingly useful internal representation, layer by layer. So for instance, or for example, in an image classifier, I want to classify an image. So maybe we have layer one, it's just going to learn and learns edges, color, gradients, and layer two learns textures, corners, simple shapes. Then layer three learns parts of objects, like eyes, wheels, handles, and layer four learns wall objects itself. So the faces, the car, the chairs. So each builds on the representation learned by the previous layer. This hierarchical feature learning is what makes deep learning deep. And it's not just about having many layers, but about learning layers of abstractions. So what are the key concepts here? I want you to just to remember and just master this key concept. The word deep in deep learning refers to the depth of learned representation. We have multiple layers of increasingly abstract feature. A deep network has many such layers. A shallow network, like logistic regression, has 0 or 1 hidden layers. So, like we have seen here, you have layer 1, 2, 3, 4. And for you to have the whole object, the faces, the cars, and the chair, you need to have the parts of the object. And then before need the part of the object, you need to know or to see the texture, the corners, the simple shape. Maybe you cannot see them, but it's hidden. That's why most of the time we call them hidden layer, because those parts is the part like you have the eyes and I can see what is just doing, but I cannot see all the operation behind what I can see, but I can just determine. So once my eyes see something, I can just say, okay, I want to classify this image. This is a dog or this is a cat. So when you are watching this or you are seeing something in front of you, you want to classify it a cat or a dog, you start by just saying, maybe you say, okay, the shape of the animal is like this, and his ears are like this, and his nose is like this, and so the color, the texture, everything. So at the end, you, with the whole object, you now conclude that this is a dog or this is a cat. So this is now, you can just go and read it, the classical machine learning versus the deep learning. This is the comparison. So this is all that we have said before, right? So in terms of feature engineering, in classical machine learning, we do it manually. So you design and select your feature. You can even say, okay, instead of 8 features, I just need 6 features. I just need 4 features. But for deep learning, it's not the case. The feature engineering here is automatic. So I cannot design and select my feature, but my network learns feature from my raw data. This is the first difference. You have the data requirements. This work well with 100 to 1,000 of sample, but this is typically needs 1,000 to millions of samples. And for the compute requirements, this is just need a modest CPU is sufficient, but this require a GPU for practical training times. And in terms of training time, this is just taking seconds to minutes, but this can take minutes to hours or days for large models. In terms of interpretability, this is often interpretable. Decision tree rules, feature importance, you can see them clearly. That's why many of the decision maker, the bank or some stakeholders, they prefer those classical machine learning because they are more interpretable. They are interpretable compared to the deep learning, which are just black box. So it's harder to explain predictions. But you can just see the result. It's just like your eyes. You cannot explain how the eyes start to determine and see this is a dog or this is a cat. But they are doing it. But behind this operation of just this saying this is a cat, this is a dog, through your eyes, you have many operations inside. So the performance on tabular data is excellent, especially for gradient boosted trees. But here, the performance on tabular data is often no better than classical methods. So if you use tabular data and apply deep learning, you are just going to obtain no better result than compared to classical methods. The performance in terms of images. Here, if you test images or training images with classical machine learning, we are just going to obtain poor without heavy feature engineering. But here it will be excellent. And in terms of performance on text, textual data, audio, or video, here it's moderate. You go to moderate result with bag of words or TF, IDF. All those concepts we are going just to come on it, where we are going to talk about textual data and how we use or we model textual data. But in terms of deep learning, it's excellent. And the risk of overfitting, it's moderate for classical machine learning, depends on model complexity. But here, the risk of overfitting is higher. Why? Because many parameters require careful regularization. So in terms of implementation, simple is very simple here, simple APIs, because we use scikit-learn here, but here the implementation is more complex. So you need TensorFlow or PyTorch. So a common misconception among beginners is that deep learning is always superior. This is a misconception. So that's why we emphasize that for tabular data with well-defined features and moderate sample size, classical method, especially gradient boost trees like extreme gradient boosting that we call XGBoost, remain the gold standard. But deep learning shines when the raw data has rich internal structure. Those internal structure can be spatial data, sequential data, hierarchical data, longitudinal data that is difficult to capture with handcrafted features. When to use deep learning and when not to use it. We use deep learning where your data is higher dimensional and has internal structure. As we said, images, text, audio, video. You have a large amount of labeled data. Typically, you have 10,000 plus samples, and the feature engineering is unpractical. If you have a case where feature engineering is unpractical and will require deep domain expertise, so you need deep learning. So if the state of the art performance is needed, and you have the compute budget, so you need deep learning. But stick with classical machine learning when your data is tabular with well-defined, meaningful features. You have fewer than 5,000 labeled samples. The interpretability is critical. Maybe you have some medical decisions that require explanation or financial decision that require explanation, like what one of us is presented yesterday. So you don't need to go to deep learning for that. You can just stick on with classical machine learning. So training time and compute costs must be minimal, and a simple model achieve adequate performance as well. So we are going to learn three architectures. Three architectures. So we introduce three fundamental deep learning architectures. Each one is designed for a specific type of data. So you have what we call the feed-forward neural network. Abbreviation is FFNN. So the input data type here is the fixed length vectors. So you have tabular data, but fixed length vectors. So the core idea is here a stack of fully connected layers. So you have many layers which are fully connected. And the example application here is just I want to predict customer churn from accounts futures. And here is a finance or bank application. And you can apply this feed-forward neural network. So it's work for tabular data, but for fixed length vectors. So you have the recurrent neural network that we call RNN, is used for sequential data, like textual data, like time series, or like longitudinal data. So you can use this one. So the core idea is like to process one step at a time, maintaining the memory. So, and you can do like an example is the sentiment analysis of movie review. So you have some movie and you want to say, okay, this movie is maybe is good or bad. So 1 or 0. Or maybe it can be violent or not violent. So you made a sentiment analysis on this movie, and it's not easy for you just to see a movie like this of 1 hour and saying, okay, this is a violent. So there are many parameters behind this one for determine if it's maybe the sentiment is good or bad or something. And you have also the convolutional neural network. This is used for spatial data. Spatial data, we talk about images or grids. So here the core idea is to slide, filter, detect local patterns. And an example is like I want to classify a clothing item from photos. Or I want to classify if an animal is a dog or a cat or something. So we need to think of it this way. FNN, here are some numbers. What category does this belong to? And RNN here is a sequence of events. What is the overall pattern? The CNN here is a picture. What is in it? So you're asking the question, what is in it in this picture? So now we have the checkpoint 3.1. So for this checkpoint, for each scenario below, which architecture would you choose and why? So you have the FNN, RNN, or CNN. Which architecture would you choose and why? So if we would like to predict whether a bank loan will default based on applicant's income, credit score, and employment history. Which architecture are we going to use and why? We are just going. Is there someone who want to reply?
Hello. I think
Yes.
it should be feed-forward network, because as the feed-forward network deals with the sequence of events. And in this bank loan defaulters, or whether the person, it based on the sequence of events, what has happened. The data collected is what has happened, the scenarios that around the people have defaulted before. So it's from there the feature you are built up to now know the conditions that will make the people to default. So I feel that it will be feed forward neural network will be the
That's
best.
perfect. That perfect. And, and also thank you, Dr. Edith. And
Thank you.
detecting pneumonia from chest X-ray images.
That one now involve pictures, images. So I think
Yes,
that one should be convolutional, what you call it, neural network.
operational neural network.
Yes,
And yes, thank you. And predicting the next word in a sentence.
that one now deal with the numbers. So I think, I mean, okay. The first one I thought supposed to be RNN, the one that goes with sequence of events. Then this one now should be the feed forward neural network for the predicting of
You,
next word in a sentence.
are you sure?
Yes, I think so.
No, but if you read when we talk about thinking of it this way, the previous point, we say RNN here is a sequence of event.
Uh,
You need to think about the recurrent neural network because here we are predicting the next word in a sentence.
no, I'm not talking about RNN in this one. I'm talking about the first one I mentioned that I said is feed forward. I said it should be RNN because it is a series of events. But this
No,
particular predicting of the next word, I'm saying that
no,
it should be.
no, here is not a series of events because you are predicting whether a bank loan will default based on applicant income, I don't know, a credit score and uh, employment history. Isn't
Okay.
it?
But I was thinking that it is now because from
It's
what
a
has happened,
yes, yes. Let's go ahead.
because where the data is collected from is from the series of events that have happened, the condition of people that had defaulted before. That is the angle from which I'm looking at it.
Yes, I see. I see. I see. But here, is it not a tabular, like a kind of tabular? Because we are talking about some numbers, and the question we can ask is what categories does this belong to? So if we are in the case where we have some numbers and we ask about what categories does belong to, because here when we want to match with this question one or this checkpoint one. So if you want to predict whether a bank loan will default, it will default or not. So it means you are asking about what category does this belong to. And
Yes,
based,
it will not be too. I think it's a binary something now. That is in the classification now. It's either
exactly,
a default or the not default.
depends on some numbers, applicant
Okay.
income, credit score, employment history.
But it's all of the number. Now, applicant income is number. I just want to get it right anyway.
Yeah,
Applicant income is number.
yeah.
Credit
Now
score may be. Hello?
I say now you get it, right?
I said applicant income is number actually. Then the credit score may be number. But now when we talk about the maybe the duration, that is the what is it called now? The years the applicant or the working experience or the years the applicant have been employed. Is it also a number? Okay, yes, it's equally a number because
Yes,
it's
but
also done in
the aim is not to predict like we don't are in a case where we have a sequence of events
okay.
and we don't ask the question what is the overall patterns. So if we ask the question what is the overall patterns, it's a case of recurrent neural network. But
Okay.
here we are in a case where we want to predict whether a bank loan will default or not. So
It's okay.
if we match it with the the tree of to choose between the tree, I think it's the feed forward neural network.
It's okay.
Thank you.
Yeah,
So
thank you.
now classifying music genres from audio spectrograms. Which architecture would you choose and why?
Music genres from audio spectrographs. Which one will
Yes.
be that one? I'm not sure of what can be used in that one.
That should be the CNN.
The CNN. Why?
I would think it's the RNN.
I go with RNN.
Yeah, me
RNN.
too.
Why RNN? So
Because
think
the audio spectrogram
yes.
contains patterns.
Okay.
So therefore, being able to classify them based on the patterns of the genre of music, the audio patterns that the spectrograms will reveal. So that's why I believe that the RNN would be the most appropriate.
The RNN. So who
Yes.
say CNN?
Okay,
Who say
so
CNN?
I I said CNN, but listening to the definition of audio spectrograms now, I think I am beginning to tilt towards the RNN as well.
Oh, okay. We say another thing. So I think here you have like just okay. Let us examine a little bit. So here you want to classify music genres from audio spectrogram. Audio spectrogram are what? What type of item? Audio spectrogram are images, right? Isn't it? So when you have like a picture and you are asking the question, what is in it? So it's convolutional neural network, isn't it?
Yes.
You get
Okay,
some
so
complication when you have seen.
personally, that was actually what came to mind. Audio spectrograms for me, more like felt like images, it felt like pictures. But the
Yeah,
definition, I think Babajide gave, just took me over the line to the other side, actually.
exact. But yes, so all the time that you are in front of any type of problem, just examine quite well for you to classify and say, okay, I'm just going to use this architecture or not, or maybe I can combine these two architecture based on the problem. So here, normally, as soon as possible or as fast as possible, you see just a picture somewhere. Just know that we are in case of CNN. And you can have a picture and then say, okay, I would like just to classify by seeing the spectrogram, by seeing the mammogram, by seeing the dendrogram. I don't know what type of gram is it, but by seeing it, I can just say, okay, I can classify this to this one. So if I have some audio spectrogram, I can say, okay, this, maybe I see the spectrogram just growing up. I can say, okay, this is maybe jazz music, because when we play jazz music, we have like a lot of maybe spectrogram or something higher. So that's why we say that this is better to use convolutional neural network. So now let us go to the main menu, as I can call it. Where is it? So neural network fundamentals. So this is the most important conceptual section, is this entire notebook. So we are going just everything that we are going to build in section 5 to 7 is presented here. So we have to take our time and make sure each concept is clear before moving on. And we start with the concept that we call the neuron itself. So the neuron is what we call also the building block. Okay, the neuron is called also a unit or a node. That's also how we can call them, is the fundamental building block of every neural network. So without neuron, we cannot say that we have a neural network. Without neuron, the neuron is the basis. So for those who are in the medical field, they study quite some neurology or some biological concept. They know what is a neuron, the central part or the unit. So this is directly inspired by biological neurons in the brain. So if you go and Google to see how the brains, the biological neuron in the brain works, so it just mimic this neuron. That's why we just use the term here, neural networks, because we have what we call some operations, the operation that we call the weighted sum or the linear combination. So we have, like, even in the brain, a neuron receives multiple inputs and computes a weight sum plus a bias term. I just give an example. Maybe I've seen an image. So for me to determine if this image is maybe a dog, I have some multiple operation in my brain to be done. Maybe I can look at the noise of the images. I say this is the type of the noise related to maybe a dog. And it's a kind of weight, okay, I'm giving to them, to everything that I'm seeing. And then at the end, I have to say, okay, at the end, this is a dog. Why you say this is a dog? Because you have many informations which makes you to conclude that this is a dog. So in general, briefly, we just note z equal to wx plus b, but this w and x, we are not just going to see the mathematical part itself here, but just note that those are weights combined to some input. And then we have the x1 explained here is the input. So your data feature, that's what you call your feature. And then let me just go there. So you have the W, the omega, some call them W, are the weights. So those are the learned parameters that determine the importance of each input. As I was saying, okay, if I say this is the noise, okay, I can give it a kind of weight, or saying, okay, this is important is maybe measure in that sense. So we have also a bias. So a bias is just a learned offset, like the intercept in linear regression that we have seen. And Z is the pre-activation value. So for this one is just what we call our first operation. And the second operation is what we call the activation function. Don't know worry, we are going just to see them practically how it works. So the neuron applies a nonlinear function f to the weighted sum. So you have this z defined here by w x plus b or omega x plus b. So we define an activation function. So where A is the neuron output, also called its activation. So just we have to note that we have a input neuron, we have hidden neuron, and we have the output neuron. So now the diagram, this is very important. You have for each input, which are the feature here, you have the weight. So this form what we call our Z here, the Z that we have seen here, the weighted sum. And always a bias. And then we apply the activation function, which gives us an output. So we have the key concept here. It looks more familiar because we have seen for logistic regression from week 5, it was exactly one neuron with a sigmoid activation function. But in this case, the inputs here are your features. So the weights are just the learned coefficient of each features. And the bias is just the intercept, and the sigmoid function scratches the output to a probability. So deep learning generalized this by stacking many neurons into layers and many layers into networks. So why do we need an activation function? This is very important to note because this question confuses many beginners. So we need to think about carefully. Without an activation function, a neuron computes like only A equals Z. So you have like this one, it's become like very simple because we don't have a F here. What have we said? A equal to FZ. So you read about function, I don't know, in secondary school, maybe in the university. A function is like you have a washing machine. So you are transforming the dirty clothes to clean clothes. It's the same clothes, but you just transform them by putting them into the machine and then getting a result with the same clothes, right? So these are the function. But if we don't have the function, we are just going to have something linear. Okay. And if we have the linear transformation, so this is a linear transformation. Now suppose you stack 2 layers of neuron without activation. So if we don't have activation, see, you have layer 1, you write it like this because we have seen that we have the weight multiplied by the inputs plus the bias. And you have the layer 2 when you have W2, okay, the weight of this layer that you multiply by Z1, okay, because here we are in layer 1, in layer 2. So this Z1 you multiply here plus the second bias. Now replace the value. You replace your value, your Z1, you know it, it's W1 dot X plus B1. So we have it here, replace. And then at the end, what we have? We multiply W2 by W1, and we multiply by X plus W2 star B1 plus B2. So what we got at the end is here is what? You have all the W2 and W1 multiplied by X, So you got the same structure like Z1, and all this become like our second bias. Okay, it means what? The result is still a linear transformation, and if it's still a linear transformation, and it's just with different combined weights and bias, so we have just different value here, but we have only the same structure has the A. So no matter how many layers you stack, without nonlinear activation, the entire network collapses to a single linear layer. So if you don't have nonlinear activation, so it means if you don't have f of z here, you have only z, a collapse to z. So you have just a single linear layer. So the non-linear activation function breaks this limitation. They allow the network to learn complex non-linear decision boundaries. This is very important to note. So, and so you have like, if you have like a curves or a spirals, your data appear like a curves or spirals, and or some arbitrary shapes that a single line or plan cannot represent. So if you have a nonlinear activation, the nonlinear activation can easily capture this structure, because this one is easy if you have like I'm using linear regression. Maybe for linear regression it's okay for me because I have just a line. But if I have maybe a curve, my data appear, when I plot them, it appear like a curve or some structure arbitrary shape. So I need a non-linear activation function. That's why we don't need to have a linear transformation at the end. So we have some common activation function. We are just going to see them by code, but let us go quickly with the sigmoid. The sigmoid is an activation function with this form. Its output is range is between 0 and 1. So the interpretation, we interpret it as a probability. Maybe you have maybe 0.8. So you say if I have 0.8, so I have maybe the form of a dog. If I have 0.1, I have the form of a cat. And it's in terms of probability. So we use it when the output layer is for binary classification. And but there is one problem with this sigmoid. The gradient become very small when this z is far from 0. So that's what we call the saturation. We are just going to see it, which slow learning. So you have the tan as well, and you have the ReLU. We are just going to see all this all the time that we are going to talk about neural network. So the rectify linear units. So you have this one. I think there is a code here. So you can visualize all those activation function and then come back to the explanation and explain to you. So just I run it. So you see the sigmoid, the form of sigmoid. They say, okay, it's between, the output is between 0 and 1. So you have in terms of probability. But we talk about the limitation of this sigmoid. We say the gradient become very small when z is far from 0. That's what we call the saturation. So we are going to see it later. And here you have the tan. The tan is with this form. So it's between, the output is between -1 and 1. And you have the ReLU. The ReLU you got like they put here, the output range is between 0 and infinity. So it's giving you max 0 or the maximum between 0 and z. So the advantage for the ReLU is very fast to compute. It doesn't not saturate for positive value. It promotes path activation, but the problem is the dying ReLU. The dying ReLU means if a neuron's input is always negative, its output is always 0, and it's stop learning. That's the problem for this ReLU. And you have all of them here. So the gradients here, what we talk about, the limitation of each of them. So the saturation is when the gradients become very small, very big. So you have the saturation. It means it cannot go beyond this. And here you have the gradient here. I'm just going to explain what is the gradient stand for. But this gradient is just obtained, just note that it's obtained by deriving this function. If you derive this function, so you will have this one. So this is the explanation. So I invite you to read about this one. So this is the observation about all this plot. So the sigmoid and tan gradient approach 0 at the extreme. So we say we are at the extreme here of the sigmoid and the tan. You see that it's going to 0. And when 0 is large, so they put it in absolute value. It means when it's negative, it will be like going to 0. When it's positive, it's going to 0. We call this the saturation. Saturation, when the gradient is near 0, weight update become teeny and learning stalls. This is one reason why deep network with sigmoid or tan activation are hard to train. And the ReLU gradient is either 0 or 1. So you have the ReLU here, it's 0 or 1. Only this one or this one. For positive input, the gradient is constant at 1, which means gradient flow through the network without shrinking. This is the main reason ReLU become the default choice for hidden layer. And the ReLU gradient is exactly 0 for negative input. Here it's 0 for negative input. If a neuron consistently receives negative input, it will never activate and never update its weight. And this is the dying ReLU problem that we were talking about. So that's why for remediating to this one, we use what we call like the leaky ReLU. The leaky ReLU is just for just remediate to this problem appearing of the dying ReLU. So a neuron in MPI. So let us implement a single neuron manually to make the maths concrete. So you need to understand the mechanism. The mechanism is very important. So let us go together and see the mechanism, how to implement a single neuron from scratch. So you have to define an input vector with 3 features. So we have here 3 features. So one data sample. So we define this input vector. So we say NP array because this is the NumPy. Okay, so we define it as 0.5. So it's like we are giving it the value for the x for each feature. And we initialize now the weight of the feature and the bias as well. So that way we define the NP random seed here for the reproducibility. So we say just we give random value, but we use here this function rand n. So we say 3. So for just saying, okay, give us 3 weights randomly. one per input feature, and also give us one bias term. We have this one, and then we can write the step one, the linear combination. The linear combination, we say it's the weight times the x, so the input. So that's why we say np dot. So because this is a we say w, it means we have x1 0.5 times the first random w1 that we have find plus till the end, okay, for our z. And then, so we can write it here. The single narrow forward pass, it's like we have the input, which is our x, and we say, okay, our weights are this one, weight coming from the w. We rewrite the w here, we have 3w. So once we are to take the first value of the w, it will be 0, because you index the index in Python start from 0 for saying the first value or the first indexes, the first index. And you have w1. This is for fe is just the flow. We call it the decimal, right? 4 decimal. So you take just 4 decimal for this value, and you have all of them, or the 3 of them here, and you define also your bias. And now you write the linear combination. So the linear combination will be written as this one. So we say the w index is 0 times the x 0, and you have this one, and plus the bias. So at the end, you plot or you print the z. So that's what we have. And here is now the activation function. Without the activation function, it will not be linear. It will be non-linear. Sorry, it will be linear. That's why we need the activation function. We have explained why we need it to be non-linear. And we use the ReLU as output. We say ReLU is very interesting when using the output. We use also sigmoids because here the objective is to compare them and to see what is just giving us. And here we use the print just for printing all those values. And let us run it. So the single narrow pass. So we have our input, our weight, random initially. So we have our bias, and then the linear combination that we multiply this one, 0.5 times 0.4967, plus this one, and plus the bias. And we got as z like 2.1316. Now we run the activation function. The ReLU give us, we have this z. So we say max of 0 and z. We replace it by this 2.1316. So we got to the maximum between 0 and this one is this. So the sigmoid function, we apply it, it's 1 over 1 plus exponential of z, minus z, sorry. That's why we replace here by minus 2.1316, which give us 0.8939. Okay, just remember, we say the output value of sigmoid is between what? 0 and 1. For tan is between -1 and 1. Tan, we apply just tan z. Okay, we have 0.9722. So this is exactly what one neural compute. So a neural network is 1,000 of these organized in layers. So this is only when we use a single neuron. So now imagine that we have thousands of this. How the operation will be complex. That's why we for the 0.44, we are just going from one neuron to a network that we call the layers. So a single neuron can only learn simple linear decision boundary, the same like you were using logistic regression. So when you have a single neuron, it's just making a linear decision boundaries with nonlinear activation. It can curve them slightly. So to learn a complex pattern, if you have complex patterns, so we stack neurons into layers and stack layers into a network. So that is just going to learn now complex patterns. So here for the layer type, we have 3-layer type. The input layer, this is not a real computational layer. It simply represents your raw input data. So if you have 10 features, the input layer has 10 nodes. And you have here the hidden layers. So the hidden layers, these are the layers between input and output where the actual learning happens. So the learning is normally here. It's like I just come back with the example of my eyes. So when my eyes is just watching an image or watching an animal for saying this is a dog or this is a cat, so it's not really the eyes that you see which is doing the operation. The operation are behind these eyes. There are many connected neurons, I don't know, activation behind the eyes that you can see, my black eyes. So those are what we call the hidden layers. They are just doing the operation. They receive the output of all neurons in the previous layers. They compute a weight sum plus bias. They apply an activation function. They pass its outputs to the next layer. They are doing many operations. So behind my eyes that you can see is like the inputs I got. So I can just, behind this one, there's an activation function for saying, okay, I've seen this color. It means that maybe this a dog of this type of race. Maybe this one, I combine this one. So at the end, I can say, oh, this is a dog. But there are many operations behind this one. And then you have the output layer, the final layer that's produced the model prediction. Its design depends on the task. Now, based on the design, you can produce the task. Let me see here. I just go a little bit far. Sorry. Okay. The output layer, you have binary classification. Okay, from my eyes, I can just classify things in binary. I can say, okay, I have one neuron with sigmoid activation for in terms of probability for say, okay, if I see these things with maybe 80%, I'm sure that I've not seen the animal quite clearly, but I'm just seeing that here's some noise, some like ears. So it looks like 80% like a dog. So I can classify it like a dog because I see all the characteristics in 80%. Okay, I had also seen in 20%, but since I'm not sure, I say, okay, at the end, it's not a dog, it's a cat, probably. That's why you use this sigmoid for the binary classification. You have also another task, which is the multi-class classification. So you have K classes, K neurons with softmax activation. So most of the time when you have the multi-class classification, you use what we call the softmax activation. So this is the output. The output are k probabilities that sum to 1. And you have also what we call the regression. Okay, one neuron with no activation. So I have no activation or linear activation. So this will be also a task for the output layer. So this is just the diagram. Maybe I have this one. I have 3 features, and for these 3 features, this is something which is hidden here somewhere. For this arrow that you have seen, there is what we call the weight here attached for this. In order for them to be connected to this hidden layer, the learner that we call the learner features. So you have 3 neurons for this hidden layer 1. And then you have the hidden layer 2 that we may call higher level feature. Maybe you can have also 3 hidden layers, maybe a middle level features. It depends. It can be 10 layers based on the complexity. And at the end, you have output. So you made the prediction with one neuron that we call the sigmoid here for the case of binary classification. Every neuron in one layer connects to every neuron in the next layer. So if you have every neuron here in one layer is just connected to every neuron here. So you have this X1 for sure connected not only to this neuron, but to this neuron, and X2 is connected to H11, H12, and also this H11 is connected to H21, H11 is connected to H22, every neuron in the next layer. So this is why these are called fully connected or dense layers. So we call this fully connected. You are going just to see in the code FC. All the time that you see FC, it means fully connected. It means for every single neuron, it's just connected to every neuron in the next layer. So you have this complexity, the fully connected layer. So here you have now the notion of the forward pass. I'm just going a little bit quickly for us to practice, but it's very important to know all those notions. And okay, I'm just going to visualize the gradients, but let us go here. So the forward pass is the process of forming prediction by passing input data through the network layer by layer. So that we call the forward pass. So when you compute a prediction by passing input data through all the network layer by layer, that's what we call the forward pass. So we start like, as I would say, you have an input X, that's your data sample that you come with. And this X normally is X1, X2, X3, X4, because you have different feature, yes. And all those features are connected to this, to all the single neuron in this hidden layer. If in this hidden layer we have maybe 8 neurons, so all the X1 is connected to all of them. X2 is connected to all of the 8. X3 is connected to all of them. So imagine all this is just going to the H2 connected again. So you have X is just here for the hidden layer 1. So you have the F of this X, this Z, sorry. And Z is writing in term of X here as the input. And H2, the hidden layer 2, is written in term of H1. So since they are connected, and our output layer now is connected, is written in terms of H2. So you have what we call here the forward pass, because it's just going from X till the Y at, okay? Where F here is the hidden layer activation. So this F here is maybe the ReLU. One of the examples is the ReLU. And G here is the output activation. So the output activation here, we choose the sigmoid. So the forward pass is fast, it's just a sequence of matrix multiplications and element-wise nonlinearity. The out part is learning the right weight. That is where loss function, backpropagation, gradient descent come in. So I'm just you two will be not randomly initiated based on how the process is just making here. It's just going to adapt about adapt it based on the training process, based on the forward pass of this neural network, the learning the right weight. So it's just going to adapt the weight. And that's where we have the notion of loss functions or backpropagation or gradient descent. Those notions come because of the hardest part of this learning the right weight, learning the right weight. And here we have now the loss function. The loss function now is just going to measure how wrong the model is. Okay, how wrong the model is. So after the forward pass produce a prediction, so we got the prediction Y at, we compare it to the true label Y. So remember, we have a true label. Initially, we sequence our data to two parts generally. We have the X part that we call the feature, and we have a target. Okay, a target which is what we call the Y, or we can call it also the true label. Okay, but when I do the prediction, I want just to be sure that my model is just giving me the result the same way I have the initial value. I take an example. I say, okay, I have 8 features. I say I have the noise, I have the areas, I have the texture, I have the color, I have this one. So my target is to say, is it a dog or is it a cat? So I have some criteria, and for that, all my data, I just take a one dog, one animal, I've seen the animal, the characteristic, and at the end I say this is a dog. I take the second one, I say this is a cat. I take the third one, I say this is a dog, this is a cat, this is a dog, this is a cat, this is a cat, this is a cat, this is a cat, or this is a dog. So for me to test my model, I don't need to use all those value or all those uh, value for my data, for my data frame. I have just to take a small part, that's what we call the training part. The training part can represent 70% of all my data. It can represent 80%. Okay, and I keep maybe 20% of my images, or I keep this 20% of my textual data or my tabular. And after running my model, and now I say, okay, I want to test if this model is really good model. So I'm just going to take one row of value or one image that I've not used when I was training, and I test and see if it's just going to tell me the same result as I have initially. So I have what we call the prediction and the true label. Okay, and if you take now the difference between this prediction and this true label, and you made, like, we can call the summation of all of them, as you have seen with the logistic regression or the linear regression, you just have what we call the loss function. Okay, the loss function, and is when you compare the prediction with the true label. So we call it also the cost function or the objective function. The loss is a single number that quantifies how far off the prediction is. So I want to see, is my prediction is really good prediction? I need to have a small loss. It means the difference between the true value and the prediction in terms of y-hat is very small when I do I say the summation of all the value that I've got. So, but now there are some common loss function. We don't say, okay, I use just loss function like this. We have some loss function based on the type of problem that you are dealing with. So you have what we call the binary cross entropy. The binary cross entropy just happen for when you have a case of binary classification. When you are dealing with binary classification, so you need what we call the binary cross entropy. So we call it the big L. This is the formula, and it's already coded for you, and you are just going to use it or just going to call it. So you can also use the categorical cross entropy. This is when you are using the multi-class classification. So you have a classification where you say, okay, this is a cat, a dog, this is maybe a rabbit, this is maybe. So you don't need, you don't have only two class classification, but you don't have the binary, but you have more than two class. You are going to use the categorical cross entropy. This is its formula. Or you can also use what we call the mean square error. We just say MSE. This is used for the case of regression. When you have the case of regression, you don't have the case of classification. So you are going just to use this one. And now, as we say, that's the hardest parts of the forward pass, we say, is to learn the right weight. So that's called, all these notion come. The notion, we say notion, remember, loss function, back propagation, and gradient descent. Now we go to back propagation. So we are going just to stop for today with gradient descent, and maybe you can have a task for you to do. And we have this one. Now the back propagation, very, very important notion after the loss. So the back propagation is just short for backward propagation of errors. It's an algorithm that computes how much each weight in the network contribute to the overall loss. So we want to know how each weight is contributing. We say the difficult part, the hardest part, is this part of learning the right weight. Because for the first weight, W1, we initialize it randomly. But for the W2, W3, it's just adapt itself with the model. It's just taking some value. and based on the pass, the forward pass. So if this learning isn't stable, but a good way for us is just to go to the back propagation, how the network learns, computes how much each weight in the network contribute to the overall loss. So it's just going to use what we call the chain rule of calculus to efficiently compute gradient layer by layer from the output back to the input. Here is just, we are just going, instead of we have inputs, the hidden layer, hidden 1, hidden 2, hidden 3, I don't know, hidden x, till the output. So the back propagation is just going to take the reverse. So we're going from the output to the input. And for going that way, we need what? So we need to do the reverse. If we need to do the reverse, we are just writing our model in terms of partial derivation. So what we are just going to see here is just to say, oh, okay, now when we compute our algorithm, how much each weight is now going to contribute to the overall loss. So for that, we have just an intuition here. The first intuition is just that no calculation required. So we just need to imagine a factory assembly line with 3 stations. We have 3 stations and the final product. So the final product is defective, what we call the I loss. If you have I loss, just remember we say it's the difference between the predicted value and the true. Okay. And if the final product is defective, it means we have a I loss. You need to figure out which station caused the problem and how much each one contributed. You work backwards. So once you have a result in the final product and you find that the final product is defective, that we are just going to match this with our neural network. You think about, you have station 1, station 2, station 3, and final product. But you find this one is defective. Why is it defective? You need to see or to figure out which station caused the problem. Maybe it's station 1, maybe it's station 2, maybe it's station 3. So it means, in other words, how each of the weights of each station contributes to this one for having maybe the defective case or the non-defective case. But for that, you are just going to go backward. So you are just going to start with the result that you have obtained and then check in the station tree if there is maybe issue here or for the weights of the station, or maybe it's station 2 or maybe station 3. So station 3, how did the last step affect the defect? So you see, you just check here if the last step, how did the last step affect the defect. So if it's here just in the station 3, I just adjust it. But here, if we are in station 2, you ask the question, how did the middle step affect station 3's output out, which affected the defect? Okay, and then I can adjust it. But if I am in station 1, I can ask, how did the first step propagate through station 2 and 3 to cause the defect? And then if I ask, it's this one is dependent to this and this. This one is dependent to only station 3. And the final product is dependent to all of them. And then I can adjust it. Now, this backward chain of who is responsible for how much is exactly what back propagation computes. So we are just asking who is responsible for how much. So that we call the back propagation. We know the final product, if it's defective or not. If the loss is higher, so I can say, okay, now who is responsible? It can be the layer 2, layer 1, or maybe the input. So each weight gets a gradient. Okay? The gradient is a number indicating the direction and magnitude of its contribution to the loss. And we adapt each weight accordingly. So if I find that there is an issue with some layer or some, so I can now update each weight accordingly, and then find now no a higher loss, but a efficient loss. It means a small loss. So the key concept here, you don't need to implement back propagation yourself. TensorFlow and PyTorch compute gradient automatically using a technique called automatic differentiation. Okay, you have just to understand the intuition is crucial for debugging and interpret model behavior. So now the gradient descent for the, just remember we say something like to adapt here or to adjust. So that's what we call the gradient descent. The gradient descent for adapting the weight. Once back propagation gives us the gradient of the loss with respect to each weight, we use gradient descent to update the weight. This one is just going to help you to adapt the weight. That's why you use the W old. W, you know it's the weight, minus you have this eta here is what we call the learning rate. Okay, the learning rate is role is to control the step size. So it's a small positive number, and here the partial derivation L with respect to W is what we call the gradient. So it's giving you what we call the direction and magnitude of the steepest increase in loss. So we subtract the gradient because we want to move downhill. So you are just going to see it with the code here. So the learning rate, you have a learning rate like when you have 1, it's too large. When you have maybe too small, it's like 0. Or 10 minus 6 or 7. It can be just right if it's 0. Or 10 power minus 3, maybe, or minus 3, 4. So this will bring your model to converge steadily toward a good solution. So we have what we call, this is a very important notion, the Adam optimizer, which we will use toward this notebook. It's automatically adapt the learning rates for each weight during training. This is why it has become the default optimizer for most deep learning tasks. This is very important. There are other optimizer, just Google it. Look at optimizers. So you can see other optimizer, what they are just doing. And we can visualize now the gradient descent. Here we use just the formula, okay? And the adapter as we just ran before. So you have here what we have, this the weight, okay? So just going that way. So you have, this is a slow, it's very slow but stable. And you see that we have this step, okay? The gradient descent step, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, you have all these steps. So you're just going this direction till going here. It's become very stable here. So you have your loss, okay? The loss is supposed to go to 0 somewhere. And this is they consider a small learning rate of 0.05. They got something slow but stable. It's slow because you see the step here. You have a point here, another point there, another point there, and just is when it's going, it just become closer, closer, closer. It means that it's slow, but it's stable. So here now you have it's converged well. You have a good learning rate of 0.3. It's converged well. It's living here, it's just going there, and then there, then it's just going fast. If you can see it, it's just fast. So if you live here, you just arrive here, it means you are just going fast. And then you have this one. And this is, we consider a too large learning rate. You see the oscillation. The oscillation is very, very significant for just stabilize here. So you have just to consider a gradient descent with an efficient learning rate for you to obtain something really stable. So this is the observation, so you can read about it. And we already tried this observation here before. Even for the learning rate, we just give the example for this one. If it's too small, too large, just what you are going to observe. If it's too small, just here, the same case here. So this is now the K training vocabulary that we have learned here. And this is very important for you to know this and to master those vocabularies. So the epoch is what we can call also the iteration. It's one complete pass through the entire training set. If you have 10,000 samples, one epoch means the model has seen all these this sample once. So it's like what we call the iteration. So the batch is now a subset of training samples processes together before one weight update. And you have the batch size. The batch size will always be 32, 64, 128. So the batch size, as we say, the batch is a subset of training sample. This also one of the strengths also of deep learning, because they are taking training samples into subset. So they are putting them like you have some, I can say some, you have some small packet of things that you put a little things so they can pass through them. You have also the step, okay, one weight update. If you have 10,000 sample and batch size, the batch size 100, so one epoch will be 100 iteration. And you have here the learning rate. We explain about it. This the step size for weight update. The training set is data used to compute gradient and update weight. The validation set is data used to monitor performance during training, so but not used for weight update. And the testing set is data held out until the very end for final evaluation. So you don't use them. So they don't never seen during training. So those data, they are not used during training. It's just for testing and evaluate. So why batches? Why not use the entire data set for each weight update? The reason is that we have the memory issue. So when you have large data sets, it will not fit GPU memory all at once. So you have now to use batches for you to put like in packets the large data sets to sequence them. So in order for them to fit the memory. So it's also for the speed. So when you compute the gradient on the full data set, it's very expensive. But if you use batches, small batches, which it will allow you to have more frequent updates. And then we have the regularization effect. Also, this is why we use batches, because the noise from using random subsets acts as a form of regularization. So it will help the model to generalize. So we have only 10 minutes. And I think that this overfitting and underfitting is very important notion for us. I don't know, Professor, maybe you are there. If you can tackle this notion or not, but I can just give you maybe a homework so you can all start to explore this notion before us to come to this one. So, Professor, have you something to say? I don't know, Professor is not there. Or have you some question or? Have you some question or is still difficult for you? But I want just to show you the exercise. So I'm just going to share it with you. And you are just going to see all those notions are very, 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 very simple. Quite difficult, but simple when you understand the basics. So do you have any question or anything to say? Hello? No question?
No questions for me.
It's difficult or too many notions?
Well, well, right now, because I'm listening to you, I will not know whether it doesn't seem to be too difficult to me. But until I sit down, rewatch this video and the recording of this video and play around with the workbook myself, then I might have good feedback. But right now, off the top of my head, your explanations make it look simple.
Yeah, of course, there's too many notions, and I'm sure that you cannot master all those notions in a single day. So you need to digest all those notions, and the best way to digest is just to exercise by yourself. And I'm quite sure that the introduction that we have given just today, it will be easy for you to continue to read this one. It will become very smooth. And the exercise part, I was just preparing another file for the exercise, but I've seen that what the professor is just giving here, all those notions that you can see here are very, very, very complete. So if you go through, we are just going to continue on that. But the most important part, you're just going to introduce the section 5 feed forward neural network itself, and now see how it's worked properly. And then
Okay.
you are just using what we call the moon, the make moon data set. It's just a synthetic data set created, but in the exercise file, I've used what we call the Titanic dataset.
All right.
So
Okay.
that is, and you can also start now to use all other type of data sets, and for you to just to train, and you are just going to see that will be easy. So for now, what I can say, just you can go to the 0.52, the practical make moon data set. So you can start just dealing with this, how it's work. You are just seeing how this you can generate and visualize the make moon data sets, and how the pre-processing is done, how everything, the splitting, and then you can go to now the feed-forward neural networks, how they define it, and then you just go. It's like it's very, very, I cannot say simple, but it's just like a music. If you know how to, you just go.
Yes.
Okay, is there anyone else who have something to say or a question before stopping here? So the notion of overfitting and underfitting is very important. You can start reading about it. I know that you already knows a little bit about this notion because you have done machine learning. So it's an important notion. That's why we just going to see after this notion how to use regularization, early stopping, dropout, all those notions, how to use them for avoiding overfitting and underfitting. So, so no question? Hello? No question?
No questions for me, sir.
No question.
Okay. We have just 3 minutes. I think the professor is going just to share with you the exercise sheet that I have prepared. But in this file, you already have the exercise on the MakeMoon dataset. But in the other file, you have what we call the Titanic dataset for the exercise. So where you have all the notions from the input data, till you have the classification that you can do. So it's just going to share it with you. So it was a pleasure for me to share this moment with you. I've seen that you were quite silencious, but next time I think that it will be more interactive, since we are just going to go to maybe more practical. But I hope that I've not preached it in the desert, and I believe in your capacity and how you can just master and digest all those notions. So see you next time, and have a nice week.
Thank you. Thank you very much. Bye.
You're welcome. Bye.
Thank you.
Bye.
Thank you very much.
Thank you.
Thank you. Bye.